Hi. So, I got few questions from my student on my WhatsApp and on my YouTube. They asked me few questions related to mutual induction and mutual inductance. So, there are three questions they have asked. One, they have asked, sir, how to find the mutual inductance of two coaxial loop. It was given that the bigger one has radius capital R and the smaller has the radius small r, and also it is mentioned that small r is much smaller than capital R, and there is two coaxial solenoid. Their length is same. The outer solenoid has n1 turns per unit length and the inner solenoid has n2 turns per unit length. Here also they have to find the mutual inductance. The third one, there is two coplanar loop. This time it is of square shape. The bigger one has greater side length and the smaller is very small compared to the bigger one. So in all these three conditions, they have to find the mutual inductance of the combination. So mutual inductance and mutual induction, there are two words. So I will explain what is mutual induction and what is mutual inductance, and we will find the answer for these questions. So let us start the mutual induction. So what is mutual induction? Mutual induction. Okay. So let us, there is a two coil. The one coil, it is connected to a battery or a variable voltage. It is a variable voltage, and I am keeping another coil and connecting it to a galvanometer, and let us insert a iron rod between them. This is a iron rod. Okay. If there is a change of current in this coil, if there is a change of current in this coil, there is an induced EMF in the second coil. Let us consider this as a coil 1 and this as a coil 2. If we change the current in the coil 1, then there is an induced EMF in the coil 2, and if the circuit is complete, this galvanometer will show deflection. This phenomenon is called mutual induction. So mutual induction, how to define the mutual induction? Mutual induction. So if there is change of current in one coil, there is induced EMF in the second coil. Induced EMF in second nearby coil. This phenomenon is called mutual induction. This phenomenon is called mutual induction. This phenomenon is called mutual induction. Okay, why does it happen? Because a current carrying coil produces magnetic field. This magnetic field lines of the first coil is linked with the second coil. And if there is change in the current in the first coil, then the magnetic field lines also changes through the second coil. We can also draw some magnetic field lines. So if there is some magnetic field lines which is produced in the first coil, that is also linked with the second coil, right? Okay. So the flux linked with the second coil, the flux linked with the second coil phi B2 is directly proportional to current in the first one. So to remove this proportional sign, one constant will come, that equal to M into. So here M is called mutual inductance. The M is called here mutual inductance. And the value of M is actually phi B2 upon I1. The flux per unit current is called mutual inductance. So its unit is Weber and its unit is ampere. So 1 Weber per ampere, 1 Weber per ampere, that we call it as 1 Henry. So the SI unit of mutual inductance is 1 Henry. So M, the mutual inductance, is a physical quantity that depends upon how the two coils are placed, how many turns in the two coils, and what material are between the coils. Okay, so mutual inductance SI unit is Henry. Okay, if and from the Faraday law of electromagnetic induction, we know that from the Faraday law of electromagnetic induction, sigma equal to minus d phi by dt. So induced EMF in the second coil is minus d phi b2 by dt, and that is minus d phi b2. Phi b2 is how much? M into I1 upon dt. Then sigma 2 is going to be minus M di1 upon dt. So in the second coil, induced EMF will depend upon two factors: the mutual inductance of the two coil and di1 upon dt, the rate of change of current in the first coil. The faster the current in the first coil changes, greater the induced EMF in the second coil. So what we have to do, we have to give the current in the one coil and we have to find the flux through the second coil, and that flux will be directly proportional to current, and a constant will come. That constant is called mutual inductance. So now we will solve the first question. So in the first question there was a loop and at the center a small loop is placed. So let us give the current in the outer coil, outer loop I, that will generate a magnetic field at the center, and the magnetic field at the center we can name it as a V1, and the magnetic field at the center of a current carrying loop is given by mu naught I1 upon 2R. The smaller has radius R1 and the bigger has radius capital R. Then phi B2, it is the magnetic flux linked with the inner coil. Magnetic flux linked with smaller loop. That is how much? This will be B1 into pi R square. So the B1 is how much? Mu naught I1 upon 2R into pi R1 square. So now phi B2 equal to mu naught pi R2 square upon 2R into I1. So this is your constant. We can compare this phi B2 equal to M into I1 from the definition of mutual inductance. If we compare 1 and 2, we can get the value of M as mu naught pi R square upon 2R. So mutual inductance of two loop does not depend upon the current in the inner loop or the outer loop. It is independent of the current or flux. Just to define it, we have written that M is equal to how much? Phi V2 upon I1. Basically, mutual inductance depends upon their radius, how they are placed. Now, I want to go to the second question, that we have to find the mutual inductance of two coaxial solenoid. Mutual inductance of two coaxial solenoid. Two coaxial solenoid. So here there is one bigger solenoid which has greater radius, and inside we have kept a that inside we are keeping a solenoid of smaller cross section. In the question it was mentioned that it has n1 number of turns per unit length, and the second one has n2 number of turns per unit length, and the length of both the solenoids are equal. So again we will apply the same formula or same method, that we will try to give the current in the outer one and we will try to find the flux through the inner one. We can do the opposite also, like we can give the current in the inner one and can find the flux through the other one. But it is more easier to do the calculation in the first way. Like generally we give the current in the outer one and find the flux through the inner one. That will reduce our calculation problem. So here suppose we are giving the current I1, then the solenoid will generate a magnetic field, and the magnetic field we can show like this. This solenoid will generate a magnetic field inside it. The green is representing the magnetic field inside it, and at the end it will spread also. Inside the magnetic field is constant. So B1 is the magnetic field due to the outer solenoid. This value will be how much? This value is B equal to mu naught N1 into I1. And the phi V2, that is the magnetic flux through the inner solenoid. That is magnetic flux through inner solenoid. Okay, so this will be how much? Phi B2, that equal to B1 into the area of the inner solenoid. Radius of the inner solenoid is R2, the radius of the outer solenoid is R1. So this is how much? B1 R2 ka square N2 into L. This is the magnetic field and this is the area of cross section. So these two will give the magnetic flux through a single turn, and number of turns per length into length, that will give the total flux through the inner one. So this is putting the value of B1 mu naught N1 I1 N2 this pi R2 ka square N2 into L. So this will be how much? Mu naught N1 N2 pi R2 ka square L and I1. This is your equation 1. Now we will compare. We will compare phi V2 equal to M into I1. After comparing, we can say that the value of m in this situation is how much? Mu naught n1 n2 pi r2 square into L. If suppose we keep a ferromagnetic material, we fill the space between the solenoid with the help of ferromagnetic material like iron, then the flux will increase and our mutual inductance will increase. Okay, now the third one. Now it's time to discuss the third one. In third one, we have to find the mutual inductance of two loop. This time our loop is a square. So this one is the outer one. So in the outer one, we will give a current I1. And we will try to find the magnetic flux through the inner one. And it was also mentioned that the outer has side length L and the inner one has side length small l, and the small l is much smaller than. Okay, so here we have to use a one formula that was in moving charge and magnetism. Using Wyatt-Savart law, we have found one formula. Let's say it is a segment of wire AB. AB is a segment of wire. At d distance, it creates a magnetic field B. The segment is making alpha from the upper side and the beta from the lower side. Then the magnetic field is given by mu naught I sine alpha plus sine beta upon 4 pi d. This formula is applicable due to a current carrying segment where d is the perpendicular distance. D is the perpendicular distance. At the point we have to find the value of magnetic field. So we can use this formula. Why I'm like introducing this formula? Because I am going to use this in this problem. So our aim is to find the magnetic field at the center due to this loop. So what we will do, we will find the magnetic field due to one side, only AB, and we are going to multiply by 4 because there are 4 sides, and we are going to use this formula. So the center is at distance, the value of D will become L by 2, and this angle is, this one will be alpha and this will be beta. Here alpha is equal to beta equal to 45. So if we apply the formula, then the B at the center is going to be how much? B at the center, mu naught I upon 4 pi. Instead of D, we will put L by 2 and sine 45, and we will multiply it by 4 because there are four sides are there and they are generating the magnetic field in the same direction. So net direction of magnetic field, we have to curl our finger along the current and thumb will point outward. So the net magnetic field at the center is outward direction. So in this situation, this is the 2 will go up. So 2 mu naught I upon 4 pi L, and this is 2 by 2 root 2 into 4. So after simplification, this 4 will cancel out, and 2 mu naught I and this 2 and upon pi L root 2. So this 2 and 2 will multiply, and 4 mu naught I upon pi L root 2, or that is 2 root 2 mu naught I upon pi L. Now it's time to find the flux through the, so phi B2. The phi B2 is how much? The phi B2 magnetic flux through the inner loop. Magnetic flux through the inner loop is how much? The B1 into how much? L square. So B1 is how much? That is 2 root 2 mu naught I. Here it's better to name it as I1, right? I1, and this I1, and this I1. So mu naught, 2 root 2 mu naught I1 upon pi L and L square. So after arranging it, this is going to be 2 root 2 mu naught L square I1 upon pi L. So this is first equation. Now we will compare it with the standard value, that is phi V2 equal to m into I1. Okay, this is your standard equation. So from there we can get the value of m how much? The value of m we are going to get the m equal to this 2 root 2 mu naught L square pi L. Okay, so these are the example based upon mutual inductance. Okay, done.